We have bad philosophy in the past that created these theories. And in the modern day, we have an abandonment of all philosophy whatsoever and all attempts to identify the deeper nature of the physical world. And so this combination leaves us with a recipe of just truly being stuck. We can't move forward. Imagine a time in chemistry before we had the atomic theory of matter. But we do have certain numerical formula for understanding how much of some substance will merge with other substances. So for example, we know that for every 8 grams of oxygen combined with every 1 gram of hydrogen, that will create 9 grams of water. And there's all these reaction ratios, such and such gram of carbon, such and such gram of oxygen, that's going to make carbon dioxide in certain mass ratios. So imagine we don't have an atomic theory of matter, but we do have these mass ratios. Dalton and other physicists came up with general laws, the law of definite proportions and the law of multiple proportions. And basically, long story short, they found patterns in these mass ratios. Now, imagine if we knew some formula for the mass ratios of these. But we absolutely refused. We were somehow blocked from thinking about why these mass ratios were the case. If we were in such a state, we might be able to take these equations of mass ratios and make deductions from them and identify further equations of mass ratios, further equations that related the different parts of these reactions to one another. You'd be able to do that, but none of it would give you physical insight into why, and we would have never gained the fundamental insights that come from knowing what's actually going on.
Hello, everyone. I'm Arkadiusz. I'm an Interintellect host. Some of you may know me already from my past salons. Definitely Jenny and Mark do know me. Today, I managed to bring another host, which is philosopher and physicist James Ellias. Hi, James.
Hey.
And today we are going to discuss philosophy and physics, especially their relationship. And the format I have in mind for this is as follows. We'll begin with a bit presentation by James, which will be basically a response to some of my questions to him, so that we introduce the topic of philosophy of physics. And then we'll start an open question session. Okay, David, no problem. And then I will open the question period to everyone and we'll discuss whatever is on your minds. Yeah, so philosophy and physics. James, my first question is, what does philosophy have to do with physics at all?
Yeah, I actually get that question when I sometimes tell someone, just what do you do for work? I tell them I'm a physicist and philosopher, and people just sort of are taken aback, like, wait, so you're saying you're like mixing a completely illogical field with a logical field, like, or a lot, it doesn't compute. So just to start things off, like, what does philosophy have to do with physics? So one of the basic questions philosophy answers is, what is the basic nature of reality? What is the basic fundamental nature of reality that we can identify simply by looking around? And so, for example, do contradictions exist in reality? Can something be one thing and another at the same time? Can a man be a woman at the same time? Can a rock be a log at the same time? Can a particle be a wave at the same time? These are philosophical, these questions rely on answers to the fundamental philosophical question of whether contradictions exist out there in reality or not. So we need to get clear on those using something that isn't physics before we use such an answer to actually answer these questions in physics. Another example, another question in philosophy that plays a very large role in physics is questions of epistemology. What's the right method of discovering science? What's the right method of discovering facts out there in reality? So what is the right scientific method? Now, someone might argue, and they have to me before, well, can't we just use science to find the right scientific method? Can't we, I forget what this guy said. He said, can't we do like a double-blind study? I'm not exactly sure how you do a double-blind study for this, but like, I understood his general point. Like, couldn't you do a scientific study to find out which method of science is the most effective? But the thing is like that presupposes any scientific study presupposes the right scientific method itself. So you'd have to use the method in order to discover the method, apparently. You'd have to presuppose the purpose of science. What is it that science should actually try to find? What kind of knowledge should science try to find? And specifically, what I mean by that, to concretize, is that in my view, science should try to look for underlying facts and underlying causes which give rise to the things that we see on the surface level. Whereas other sciences believe that we should simply produce, other philosophies of science believe that we should simply try to produce systems of prediction, ways of predicting the phenomena we see around us. And there's other views of what science should do, and all of these are philosophical views. You can't use science to identify the answers to these questions, because to use science is to presuppose answers to these questions. What should science try to find, and how should science proceed? By what method should science proceed? So that's metaphysics and epistemology so far, two branches of philosophy that are indispensable in the right way to do physics. You can't look into the physical world for answers to these questions. You have to think about them separately. Now, you of course can use data from the physical world, and data, you can use the evidence of that, but you need to think about these concepts separate from the scientific method itself, because they determine the proper scientific method. They determine the basic assumptions about reality that you bring to that investigation. Again, epistemology and metaphysics in play there. Now, one thing that's going to be important to a physicist, that any physicist, a lot of stuff gets called philosophy among modern physicists that isn't really philosophy. So this is a clarification. A lot of times among physicists, philosophy gets equated with what I would call deeper physical meaning. So for example, we're going to get into this more in detail if you don't know what this is, but consider the difference between the Copenhagen interpretation of quantum mechanics and the pilot wave interpretation. Again, if you don't know what this is, don't worry about it. We're going to go over it in a moment. This is just a point for scientists. The Copenhagen versus pilot wave views, these are two different views of what is physically going on in a quantum system. To put it shortly, the Copenhagen view is that quantum systems are both a wave and a particle at the same time somehow, that they exist in that contradictory state. And the pilot wave theory, put shortly, is that there is no contradictory state. There's a wave that pushes particles around. Modern physicists will often say the answer to this question of which one's true doesn't matter. It's just philosophy, is what they'll say. Philosophy is a way of explaining that it doesn't matter. And they're basically saying these are deeper questions. It's not our, like at best, it's not our department. At worst, it just doesn't matter to anyone, because all we're here to do is to make correct predictions, and we don't need to answer these quote unquote philosophical questions in order to make correct predictions. Now, notice that that in and of itself is a philosophical position. It's simply a philosophical position which remains unexamined because of certain assumptions simply being made and written off as non-philosophical, written off as simply that's the way science is, so we're not going to question that. That's just what we do. Philosophy studies the questions which need to be answered in order to gain certainty about these questions in physics. And philosophy has to be differentiated from physical meaning. And often physical meaning is confused with this. And, modern physicists will say that, the Copenhagen interpretation versus the pilot wave interpretation, notice how they don't even call it a different theory. They call it a different interpretation of the same theory, but these are different theories. They make different claims about the physical world. They make different claims about the physical world. They make different claims about the physical world. Now, because our host hasn't returned, I'll go ahead and field questions. We have an additional question from Robert, and he asks, doesn't the Copenhagen theory describe behavior as well as wave-like in some contexts and particle-like in other contexts? Yeah, that's true. Now, part of the claim of the original Copenhagen interpretation, you'll notice I accidentally say their words sometimes, and that's just an error. I was educated under this system, so I sometimes default to these words, and I hear them all the time. The Copenhagen theory, it does treat the particle as a particle at some times and a wave at other times. That's true. So one thing that you can do, and this has been done, is to ignore the claims that at rock bottom there are contradictions in reality. That is basically what modern physicists do. They say, okay, look, there was a bunch of philosophical ooga booga associated with quantum mechanics when it was first created, and that's true. But we're going to ignore that ooga booga and just stick to the observation, and just stick to the predictions that quantum mechanics makes. And such a view does remove the contradictions, but the problem is it removes all of the physical theorizing about what is actually going on also. So that is a problem, and to ignore the physical interpretation is to have a philosophy to begin with. And we're going to get more into that later. Arkadiusz has returned. What's your next question? So I just finished explaining all of the different ways philosophy is important to physics. So what did you want to ask me next, Ark?
Yeah, so excuse me, everyone, first of all, for my sudden disappearance. My laptop simply couldn't handle the heat. I grabbed another one that is more heat resistant. And so now we are all coming back to where we finished. And so my next question, which we already, I think, delved a bit in, is how do contemporary physicists think about quantum phenomena and gravity?
Right. The two theories for these two subjects are quantum mechanics and general relativity. Now, I like to draw a distinction between quantum mechanics and quantum phenomena. And I like to draw a distinction between general relativity and gravitational effects. There's a distinction between the phenomena we're observing and the particular theory that we use to understand those phenomena. And this is an important distinction to me because I believe that our current theories for understanding these phenomena are flawed. So we don't want to equivocate between quantum mechanics and quantum phenomena, because especially if quantum mechanics, the theory is wrong, or rather I should say flawed, because there's some sense in which it's right, and it has to be right since it gets correct predictions. It does get correct predictions. Now, what is it? So how are these theories thought of? I think both of these theories, quantum mechanics and general relativity, are flawed in similar ways. First, for quantum mechanics, in the modern day, it's really thought of by most people and used by most people as simply a theory that gets correct results. It talks about basically what it describes is this wave that changes over time. So think of a wave squiggling, and that wave changes in shape over time. And this wave gives the probability distribution of where a particle is to be found if a measurement is done. Okay, now, once a measurement is done, the particle will then be found at some location at some location given by that probability distribution. It can be found anywhere within that probability distribution, but it will be found somewhere within it in accordance with that probability distribution. So, in accordance with that probability distribution. Now, what's interesting, now something that has been brought up is, what is a measurement? What do they mean by measurement? And basically, the theory is unclear about this. A lot of people, this is called the measurement problem, and a lot of calories have burned over this. And this is something I simply am not interested in talking about. I'm not interested in solving the measurement problem because I don't think it's framed properly. Because I think the whole theory, the introduction of measurement into quantum mechanics, into a theory, is just flawed to begin with. One of the major flaws of quantum mechanics, if not the major flaw, is that it doesn't attempt to describe the actual facts of a physical situation. It describes instead our knowledge of a physical situation. Now, in some sense, that's fine as simply a predictive model, but if that is the case, it needs to be treated as just a predictive model. And it is not. It is treated as some kind of halfway in between just a predictive model and the actual theory. People treat the quantum wave function as this actual thing, and because maybe it does relate to an actual thing, but no one is clear on exactly the reality or non-reality of this quantum wave function and how it changes with time. So really what's required, I think, is a stepping back and an attempt at a completely new theory that identifies facts of the matter. Now, one alternative that exists is the pilot wave theory, which, to answer a question you asked Bruce asked, have there been attempts to prove the pilot wave theory? I'm unaware of any attempts to prove the pilot wave theory. I don't believe there are any cases where they've been able to do an experiment where quantum and the pilot wave theory get different results. Now, however, the pilot wave theory does make an actual hypothesis about what's going on physically. It says there's this wave, the wave pushes a particle around. There are particular initial conditions that aren't known about the particle, and so we don't know exactly how the particle will end up getting pushed around, and those unknown initial conditions lead to the randomness, the quantum randomness that is actually experienced during measurement. And so that is a physical theory of what is actually physically going on. And incidentally, measurements are just seen as strong interactions under that theory that actually change the nature of the pilot wave. So in that theory, we have an actual physical picture of what's actually going on, but the theory doesn't do anything that quantum mechanics doesn't already do. Now, for general relativity, we have a similar problem, which is that the theory describes what different observers will measure when those observers go at different speeds or are in different gravitational fields. So, for example, what the special theory of relativity will tell us, it'll tell us if you're moving really fast, say with respect to the Earth, and I'm stationary with respect to the Earth, then you will measure lengths and durations as being a certain way, and I will measure those same lengths and durations differently, but it doesn't explain why. It's just an account. It's just the theory is nothing more than an account of how different observers measure things differently. It does not go into the physical cause of this difference. And by either by explicit statement or by implication, the view is the lengths and durations are actually different for different observers. The two observers are both right, is what we're told. And in some sense, that's true. The different observers are measuring them differently, but there's no account for why they're doing that. So let me give why they're measuring them differently. So let me give an analogy. If you and I heard someone. Nope. So I thought I heard someone asking a question. So imagine you and I are vastly different heights. Imagine I'm a super short guy, you're a super tall guy, and we're both looking at a fish in a lake. We will be looking at that fish from very different angles in the lake. Now, you may know that because of the way light works when it goes from water to air, the fish will appear to be a different depth for me than it will appear for you. Okay, now the fish is, of course, only at some particular depth. It's not at both depths at the same time. What general relativity does is analogous to this. It will describe how different heights, it would describe how different heights would lead to different depth measurements, but it would not tell us why we have different depth measurements. It would basically say the fish is such and such deep for me, and it's such and such deep for you as a result of our differing heights. In like form, what general and special relativity say is they say, you know, the length of this object is such and such for you because of your state of motion and because of your exposure to gravitational fields. And it's such and such different length and duration for me because of my relative velocity and my exposure to gravitational fields. So it's analogous like that. Now, what we really need is something analogous to the theory of light we have now, which is it explains why we have different depth measurements for different observers. It explains that the light changes direction. It goes from the fish into the water, into the air, and as it goes from the water to the air, the light changes direction, which leads to the difference of depth measurement for me and for the tall guy. So what we need is something like that, or at least a theory that still predicts observations, but is open to the idea that there is still some underlying cause we have not yet identified. And as I'll argue further later, the form of these theories close us off from identifying these further physical facts which give rise to the difference in observations.
Let me know if I'm wrong on this, but as far as I remember, yeah, that's Einstein changed his views between special and general relativity. And in special, there is no attempt to explain, is there really some change in time or space? And in general relativity, there is a genuine claim that, yeah, there are changes in space and in time. Time does indeed dilate and space contract. Yeah.
I'm a little can you say the question again? I'm a little unclear on the question.
There is Einstein changed his views on the method of science between special and general relativity. So
yeah, he did.
At the time of special relativity, his view was that the aim of science is simply to come up with some mathematical recipe that are good tools to make predictions. And then he changed his view to say that the goal of science is to discover what is the case. And so is it the case that special relativity treats those supposed change? It doesn't believe in those changes in time and space, except in terms of how simply different observers observe things. And in general relativity, those changes are treated as genuine changes. So general relativity actually claims that space contracts and time dilates.
I see. Yeah, I see what you're saying. So, yeah, in some sense, that's true. The theory still talks about how different observers measure things differently depending on their gravitational fields, and again, doesn't give a specific underlying cause, like a specific account of the underlying cause for that. But there's sort of a general account. It doesn't explain exactly how it works, but there is a general account of simply saying that these coordinates simply change. And first of all, like, this is more physical in a sense. It's more of a causal theory that tries to identify actual underlying causes. The problem with general relativity is space is not a thing that can contract, and time is not this thing that can dilate. What's going on is that all we know for sure is that lengths are being measured as shorter or longer, and durations of events are being measured as shorter and longer. So it's really important to understand this. Now, this is where there's a physical misunderstanding of what time and space actually are. Time and space are not this place where entities and events live. A lot of times when physicists think about general relativity, they'll often draw a special or general relativity. They'll draw a space-time diagram with length, some sort of length measurement along the y-axis and a time measurement along the x-axis. And different locations on this diagram represent events that happen at different locations and at different times. And what will happen is as we change perspectives, or as the gravitational field as the space is exposed to a gravitational field, these lines, the grid lines will change. Okay, now these grid lines are showing us how length and duration measurements change for different observers, but that is completely different from some kind of claim that space itself or time itself is being changed. Space and time are not this cosmic graph paper. They're specific space. There's no evidence for space existing apart from the fact that there are physical relationships between events. This is 10 centimeters away from this. That is the fact that gives rise to the abstraction of space. And to say that like space itself is warping, it just simply doesn't make any sense. We can talk about the distance between objects changing at different locations for different reasons. We can talk about the duration of a certain process changing. But to say that time itself is changing is a mistake. So yeah, maybe there is, I actually hadn't thought of it that way. Maybe there is a more physical attempt to get at the basic nature of reality in general relativity, but it has this flaw. So that is my view on that, and why general relativity needs to be replaced as well. So Robert's saying, I thought that in general relativity, the changes in space and time measurements are caused by the distribution of energy and matter, and the detail is expressed by means of field equations. Yeah, that's correct. So the way masses are distributed will cause differences in length and time measurements for different observers. And the way that that's thought of is differences in space and time. But the real question is this, like, space and time aren't these things that can bend. There's no cosmic graph paper. All that's going on is that the measurements of these different things are changing. And the question is why? Why are the measurements changing? Now, going back to the fish example, the reason the measurement of the fish's depth changes is because light changes direction, and there's a difference in angle, and that causes a difference in depth measurement for the tall observer versus the short observer. There's a physical process by which that happens. We need to understand the physical process by which these differences in length and duration measurements are happening. And the current theory blocks us off. The current theories in special and general relativity blocks us off from that information.
So to follow up on the discussed issue, maybe a question that many would ask is, many people have tried to claim that those measured changes are not real changes, and they invoked something called ether, but wasn't ether disproven?
So first, let me make like a correction in your question. Those who think that there's an ether, they don't think that the changes in measurements are like fake or somehow an illusion. Basically, let me introduce you to the ether hypothesis here. So at least this is a specific kind of ether hypothesis called the Lorentz ether theory. So one reasonable hypothesis is that these changes in measurement are caused by the following process. First, that there's a kind of medium throughout space. There's this medium throughout space called the ether, okay? And for a little bit of background, the reason we would think that there's the evidence for an ether, there's already prior evidence for an ether, which is that light is a wave that can wave in vacuum. So when there's apparently nothing out in space or in a jar, with all the air sucked out of it, you can still see things in space. You can still see things in the jar. So that wave of light is somehow traveling through nothing. Nothing in quotes here, because nothing isn't a thing. That's sort of a separate metaphysical issue, though, to talk about. But basically, there is, I think, conclusive evidence that there is an ether. There is this stuff that's everywhere. And one hypothesis that would explain the relativistic effect would be the following: that when an object moves, I'm sorry, let's think of it this way. When one object is moving with respect to another, okay, remember, motion is relative, so we can't say just, oh, one object moves, full stop. We have to say one object moves with respect to another. So imagine two spaceships. One of them you think of as stationary, another one you think of as flying through space. Each of these spaceships is going to have a different speed relative to the ether, right? Like, because the ether might be blowing through this image. There might be like an ether wind blowing through this image. So the one that we think of as stationary, there might be an ether wind. The ether might be moving with respect to that quote unquote stationary ship. Okay. So, but the point is that these two ships travel through the ether at some different velocity. Lorentz ether theory makes the hypothesis that when an object moves through the ether, its lengths become different as a result of motion through the ether. And its internal processes slow down the faster it's going through the ether. And incidentally, there are arguments for why this would happen. This isn't just some kind of made up hypothesis like, oh, well, maybe, maybe it shortens when it moves through the ether. No, Lorentz actually derived like a length contraction for objects if it were to move through an ether, and a time and a duration dilation for the processes within objects. He deduced them from the existing laws of electrodynamics. So there was precedent for this. It wasn't just this ad hoc assumption. But wherever the hypothesis came from, let's just think about the hypothesis. So different objects moving through the ether at different speeds will be contracted differently as a result of their motion through the ether. What this would then lead to is that these different objects would make different length measurements. Why? Because their rulers are different sizes. Now, what's interesting is they don't notice this. They don't know. No one would notice that their ruler was a different size as a result of their motion through the ether. Why? Because if you look at the ruler, your eyeball is contracted in the direction of the ether motion. So the ruler would appear to look the same length despite your motion through it, because your eyeball is being affected exactly in the same way as the ruler is. So all of your rulers would look normal. However, other people's lengths, say the spaceship that you see moving with respect to you, it's moving through the ether at a different speed. And as a result, it would appear, and it truly would be, a different length as measured by your instruments, because your instruments are the way they are because of that particular motion through the ether. And his lengths and his instruments are a different length because of their differing motion with respect to the ether. So there truly is a different comparison between your rulers and his ship as a result of that different motion. Now, this is a truly causal hypothesis. It has a chance of being correct. And to put it briefly, under this hypothesis, gravity would be described by perhaps gravitational objects sucking the ether in, thus causing ether motion near a planet. And, you know, us standing on the planet right now, we experience a certain amount of gravity because the ether is flowing through us, pushing us down, to put it crudely. But that would also cause time dilation. And according to general relativity, the stronger a gravitational field, the slower the durations will go. And this would be described by simply the ether is moving quickly through your body, and so your internal processes go a little slower as a result of that motion. So that would be such a theory like that. That would be a truly causal way of thinking. That would be a truly causal way of thinking. And this all relies on an ether, the existence of an ether. Now, you asked me, was the ether disproven? The consensus right now among scientists is that the ether was indeed disproven, and they'll point to a common experiment. They'll commonly point to a certain experiment called the Michelson-Morley experiment. But it's worth noting that the Michelson-Morley experiment simply did not disprove the ether, because its result, basically, I'll just say, to say it quickly, this Michelson-Morley experiment attempted to measure the speed of the speed through the ether. Okay, it attempted basically, the Earth is going around in circles around the sun. So that means that at different times of the year, it should be going at different velocities with respect to the ether. You know, sometimes it might be going upwind, other times it might be going downwind. So there's going to be this change in velocity depending on what time of year there is. Well, they made these measurements to try and discover the velocity through the ether, and there was no change. According to their measurements, we're always basically stationary with respect to the ether. There was no measurement of the velocity. So that's sort of the simple way of coming at this. Now, first of all, this doesn't disprove the ether. Like, before getting into the details of the physics, let's just start with basic facts. There is no way to disprove the ether. The ether has already been proven. The ether's already been proven. You can't disprove it. And here's why. That might sound kind of like dogmatic or something. But here's why. We already know that there are waves in vacuum. We already know something is waving. You can't have a wave of nothing. Nothing is not a thing. First of all, there can't be nothing. Nothing isn't a thing. So you can't, when we talk about the vacuum of space, what we should really be talking about is like, it's the absence of certain kinds of entities, such as matter. There's an absence of matter. That's fine. If that's the word, that's the word we should attribute to vacuum. Vacuum should not mean nothing, because nothing isn't a thing. Nothing is not a positive thing you can talk about. If it was, it wouldn't be nothing. So there is no nothing. Okay. Second of all, there are these waves out there. Waves are an increasing and decreasing phenomena of certain properties. You can't have increasing and decreasing properties of nothing. Nothing doesn't have properties. So there has to be something there. So the existence of light waves proves the ether on its own. Nothing you can say after that can possibly disprove it. Now, but there might remain a legitimate question in your mind. Well, like how could they not measure the speed through the ether if you insist that there is one? Okay, yeah, good question if you're thinking that. The answer is that Lorentz ether theory was motivated by the desire to answer this question, actually. And the way it answers this question is by saying that because objects contract when they move through the ether, and because their internal processes slow, because durations dilate, because of this length contraction and duration dilation, different observers will measure speeds differently as a result of their motion through the ether. Because the way you measure a speed is by measuring a length and then by measuring the amount of time it takes to traverse that length. Now, what ends up happening, according to Lorentz's transformations, which remember, Lorentz derived these transformations from earlier laws of physics. He didn't just make them up to save the ether. Well, he may have done that, but he derived them from actual earlier physics in electricity and magnetism. She always thinks that when I say that word, I'm saying her name. So anyway, that's she who shall not be named. Okay, so what are the effects? So when an object moves through the ether, because of these effects, their lengths shorten and its durations change. And as a result, speed measurements are different. And as a result of these differing speed measurements, it all cancels out to make light be measured to be the same speed, no matter how fast through the ether you're going. And as a result of that, we cannot identify our actual speed through the ether. So that is one hypothesis that has a chance of being right because it doesn't ignore the fact that the ether has to exist. And simply all that happened is that Einstein came up with a theory that ditched the ether and simply described the differences in measurements between different observers. So there was no disproof of the ether. It is just that scientists philosophically preferred Einstein's way of thinking about it.
Let's maybe move a bit from gravity, from general and special relativity to quantum theory. So we've made comments about how we can think differently about large-scale theory of gravity, but we often, when hearing about quantum theory, hear some claims that particles are in different places at the same time. So basically, we hear claims that at the bottom, reality is in some way subjective, contradictory, doesn't obey the law of causality, or even indeterminate, where there is no determinate location, let's say, of a particle. How do you think we should approach these claims?
So first of all, that's actually a good way to put the question. It's not like what's the right answer. You say like, how do we approach this? Because I don't think you could get the right answer to these questions without the right approach. And the right approach is an inductive approach. That means you don't jump directly to theorizing. You start by looking at the actual observations. So many people read some stuff in textbooks, watch some stuff on the Discovery Channel. Well, let's not talk about that, but let's talk about people who are really thinking about this seriously. They read from textbooks, they absorb certain theories without identifying the observations which gave rise to those theories. They then reason from those theories and they conclude, oh, well, it must be subjective. Or rather, like the particle must be in multiple places at once, because that's like an indispensable part of the way the theory looks at things. But if you look at the actual history, if you look at the actual observations that were made that gave rise to these flawed theories, what you'll find is that you don't need to interpret these observations to prove the idea that a particle is in two places at once or is in a contradictory state. Specifically with quantum mechanics, what's basically going on is, as I said before, there's a statistical probability distribution. There's this wave, and the places where the wave has a high amplitude are places where the particle is likely to be found, and the places with a low amplitude are places where the particle is unlikely to be found, okay? Now, one way you can think about that is that the particle is in multiple places at once, that it's like, I don't know, a kind of, imagine, this is the example that I kind of gave myself to think about the way they're saying that. The particle is like a ninja in a dark barn with a strobe light. I don't know if you've ever been in like a dark room where a strobe light is going on, but like if people are moving quickly with a strobe light, it appears they're in one place, then suddenly they appear to be in a different place. Okay, so like you can think of the particle as sort of like teleporting to all of these places very quickly. And so it's like in multiple places at once, and it teleports to a certain part of space more often, and so it's more likely to be measured at that location. It teleports to other locations less often. notice how even my analogy requires the particle to be in one place at one time at any given time. You literally can't think of it as multiple places at once. But here's the thing. We don't have to think of it in any particular way. We don't know why the probability distribution is the way that it is. We just know that this probability distribution gives correct answers. It doesn't tell us that the particle is actually spread out over multiple places at the same time. So that is just people reading their own subjectivist philosophy into the observations. All we know is that there's a probability distribution. And incidentally, this view that I just gave, like all we know is a probability distribution, and like the evidence doesn't support the idea of contradictory states. At this point in history, this is actually a pretty mainstream view. If you like ask Neil deGrasse Tyson, for example, just someone who's like just the epitome of just an absolute mainstream thinker, Tyson explicitly thinks that like one should conform to the mainstream as a matter of good epistemology, incidentally. He's like in some sense opposed to thinking about scientific issues on your own. He doesn't think that the particle's in multiple places at once. So the old view that was developed in early quantum mechanics is kind of on its way out. The problem is that there kind of is no philosophical view anymore to fill the void. So it's pretty well established that the particle isn't in multiple places at once. It doesn't necessarily involve contradictions. A lot of physicists still think that, but that view's on its way out.
Yes, and from myself, I can maybe add that it's also, I think, basically disregarded as a hypothesis among philosophers of physics. For example, in a very popular textbook titled Philosophy of Physics and Theory by Tim Maudlin, he is a very respected philosopher of physics and goes throughout the book explaining different explanations of the same equations of quantum theory, namely whether there are many worlds, that's particles, instead of being in two places at the same time in the same world, actually a new world is created, so the reality splits into two. He goes through other theories, the mentioned pilot wave theory, and what he doesn't even go through are those claims often called Copenhagen interpretation, which is that particles are in different places at the same time. And he says that this is not even worth commenting. So, so even this view is often portrayed in media in kind of a sensational way. It's either completely out or on the way out. Yeah. That's something I wanted to add. That's another thing that you've also already covered, but let's dive deeper into it, is how did philosophy play a role in those different ways of thinking about physics?
Yeah, so yeah, this is kind of circling back to, you know, what role philosophy has in physics. And so specifically, how did we get here? Specifically, you know, how did we get to these flawed views of physics? And it's essentially bad philosophy. So in metaphysics, in the branch of philosophy that deals with the basic constitution of existence, in quantum mechanics we have primacy of consciousness. Again, it's the idea that our minds create existence. Something that you would hear in Niels Bohr, who is one of the founders of quantum mechanics. Again, founders of quantum mechanics, not founders of those phenomena, but a founder of a particular theory trying to understand it. What Niels Bohr would say is, he said, the particle is in no particular state until it's measured. And the implication of this really is that, like, until a human mind comes into contact with that stuff out there, the particle isn't any particular way. So what we have right now is a theory which was born of radical subjectivist philosophy. Okay, now, as we just said, this subjectivist philosophy has lost popularity. However, what we now have is a kind of pragmatism, basically. In the modern day, we have a non-philosophical perspective. And that non-philosophical perspective is, at least among physicists, there might, I actually don't know the debate among philosophers how this works. I get the sense that a lot of philosophers of physics are doing the actual physics now. I don't get the sense they're doing it well. It doesn't seem to me like they're making any progress, but at least they are doing a little bit of physics. They're thinking of the issue physically. And then because of the way words are used today, they call it philosophy. And Tim Maudlin would be an example of this. So the modern perspective among working physicists is to reject the postmodern BS that consciousness creates existence and forces the particle to be in some particular place, that your mind has something to do with the measurement, for example. Instead, what they've done is they've taken a pragmatist approach, which is basically, as long as our theory gets correct answers, it doesn't matter what the result is. I'm sorry. As long as it gets correct answers, it doesn't matter what the theory says. They strip the theory of all physical meaning and simply say, does it get correct results or not? Can it make novel predictions? And these subjectivist theories, they do make the correct predictions. And so all that's done is that they're stripped of their subjectivism, but at the same time, they're stripped of any deeper physical meaning. And this attitude simply leaves us stuck. It simply leaves us stuck and unable to go deeper. We're unable to say, if we were to hypothesize along the lines of Bohm's pilot wave theory, then we'd say, okay, there's this wave pushing the particle around. What's the wave a wave of? How is that wave affected by other kinds of waves, maybe gravitational waves, maybe like other kinds of quantum waves? How do these waves interact with one another? What kind of mediums could support waves could wave in this particular way? We could ask questions like that, maybe, but those questions are really closed off to us because all we say is, oh, well, we have this set of mathematical abstractions that get the right results. And so we're simply stuck there. So what we have essentially right now is we have bad philosophy in the past that created these theories. And in the modern day, we have an abandonment of all philosophy whatsoever and all attempts to identify the deeper nature of the physical world. And so this combination leaves us with a recipe of just truly being stuck. We can't move forward. Imagine, to understand this situation, I'll take us back. Imagine a time in chemistry before we had the atomic theory of matter. Imagine, I think this would have been roughly the year 1800, maybe like 1820. I don't remember my dates on this perfectly, but imagine something like 1820. We don't yet have an atomic theory of matter, but we do have certain numerical formula for understanding how much of some substance will merge with other substances. So for example, we know that for every 8 grams of oxygen combined with every 1 gram of hydrogen, that will create 9 grams of water. And there's all these reaction ratios, such and such gram of carbon, such and such gram of oxygen, that's going to make carbon dioxide in certain mass ratios. So imagine we don't have an atomic theory of matter, but we do have these mass ratios. Dalton and other physicists whose names escape me at the moment came up with general laws, the law of definite proportions and the law of multiple proportions. And basically, long story short, they found patterns in these mass ratios. Now, imagine if we knew some formula for the mass ratios of these. But we absolutely refused. We were somehow blocked from thinking about why these mass ratios were the case. If we were in such a state, we might be able to take these equations of mass ratios and make deductions from them and identify further equations of mass ratios, further equations that related the different parts of these reactions to one another. You'd be able to do that. but none of it would give you physical insight into why, and we would have never gained the fundamental insights that come from knowing what's actually going on. Once we knew what was actually going on, it opened the door to all kinds of combinations of matter which never would have been possible before. So like, nanotechnology, an understanding of protein folding, a deeper understanding of organic chemistry, understanding how different organic molecules will actually, all of this would have had to have been understood one step at a time. A lot of it probably would never have been understood without this broader theory. And who knows what kind of knowledge is waiting beyond this quantum veil if we were to actually penetrate it by thinking causally, by thinking of the underlying structures that give rise to these mathematical patterns that we're currently aware of. So that's the analogy I would make for our current situation in physics. And the philosophical cause is a faulty theory in the past, followed up by basically no philosophical theory in the present of what these things actually mean.
Before we jump into open discussion, my only comment would be that this lack of philosophy is actually a philosophy.
Yes.
And not simply in some technical way, meaning that rejection of philosophy is kind of philosophy, but in actual case, at the beginning of the 20th century and at the end of the 19th century, we had many philosophers in Germany, in particular, where the quantum theory was being developed, where they actually advocated that we aren't able to explain what's behind observations. They had very skeptical views and therefore advocated for a view that's called today in philosophy instrumentalism, with the idea we've already covered, the idea that scientific theories are instruments for practical purposes. And so they did advocate that idea. And so those figures are, I think, mostly among the movement called logical positivism, which I think many of you have already heard. So those are actually philosophical ideas. And as James said, this is to a significant degree still holding among physicists, but I think among philosophers of science in general, not only philosophers of physics, I think this view doesn't hold anymore. I think the most popular view right now is called realism about scientific theories, meaning that scientific theories attempt to get at what really the case and not simply be instruments. I think it's a good time to open the discussion to the audience. So whatever any of you would like to discuss, you're free to raise your hand or put your question in the chat if you prefer that. And yeah, let's have actually a formal salon, because salons are were actually group discussions.
Go for it, Jonathan.
Well, good morning from where I'm calling in from. You mentioned, I think, that in general relativity, at least the way you think of it, it's wrong to think of it as space expanding, but rather than just things themselves moving apart, if I remember that part correctly. First of all, is that right?
No, it's not that space is expanding per se. It's that certain lengths are getting longer. Yeah. Right. So like because again, space isn't this cosmic graph paper. There's no such thing as space except for relationships among entities. So like the lengths of things literally get longer or shorter because and the way to think of that is like the distance between their edges gets longer, and then perhaps also the length between entities might change as well due to gravitational fields as well.
Sure. And then so how does that how would you connect that with, let's say, cosmic expansion, like of the universe, over cosmic time?
I do not know. I simply don't know the answer to that question because part of my approach that I didn't get into today is that I have an inductive approach, which means like I only start with the observations and I only accept ideas for which I've seen the observations and reasoning steps that give rise to their proof. And I have not seen the observations and reasoning steps that give rise to the proof of cosmic expansion. I'm vaguely aware of the Hubble redshift. I know about that, but I do not know what causes it. The idea that everything is getting further away from everything else, sure, that sounds plausible, but I really don't know what other explanations might be out there that would explain this redshift. So I couldn't make that relationship because it goes beyond what I actually know.
Okay.
And I suspect it goes beyond what like everyone knows. I don't know. Maybe someone out there really does understand it, but I'm skeptical. I think a lot of people are standing on the shoulders of prior giants without understanding what those giants did. So they're not really earning it. They're not really standing on their shoulders. They're unable to reason from those prior achievements because they don't know the proof of it. And part of my project is to actually reconstruct that proof in order to properly reason from those early achievements, if they are in fact achievements.
Yeah, I would say nobody knows the cause for the cause of dark energy, of why it happened. We're at that phase of our universe.
Yeah, dark energy is a different issue, and that dark energy is the proposed cause of why the expansion seems to be accelerating. And that's, I mean, and it's one, and now no one, it's not, you're right, Greg, no one is claiming to know the cause of dark energy, but my point is deeper than that, is that I don't even understand the cause of the Hubble redshift. Other people might. I'm just saying for myself, because I haven't seen the inductions myself, I can't make a statement on that. And I'm skeptical of those who do, is all I would say. I'm skeptical of those who would claim that they're completely certain that, every object is getting further away from every other object, or the universe is expanding or something. I'm skeptical of those claims. Not saying they're wrong. I'm saying I would have to see the full evidence and reasoning steps that led to them.
Sure, understood.
Yeah. Other questions? All right, we got a written question from Robert. Might particles and waves that are perceptual properties of macroscopic entities not be applicable to microscopic entities? Maybe microscopic entities will need to be described by different properties and terminology. Okay, so let me, that's maybe a little tough question to understand. Let me try to reword it so it can be understood better verbally. I'm going to restate the question. Perhaps okay, I'm restating the question. Particles are a concept that come from observing macroscopic phenomena, such as specks of dust or bouncy balls. Maybe, could it be the case that microscopic entities are not like this and will need to be described with different properties and different terminology? Absolutely. I think this is something that we really have to consider as we move forward in physics, because let's see, when we go down to the quantum level, what we see is when we zoom in on entities very closely. So for example, when we zoom in on the electrons that somehow move around the nucleus of the atom, we find that their behavior is wave-like. We find that, they exist in an energy relationship with the nucleus. What do I mean by energy relationship? I mean that negative electron is attracted to the nucleus, and to break it off, it's attracted because one's negative and one's positive, right? And to break that electron off of the nucleus, to ionize it, requires energy. It requires motion. You have to deliver motion to it in the form of heat or in the form of light in order to actually break that electron off. But the nature of those energy relationships is wave-like somehow. Yet, when this entity, when this electron rams into a detector screen, the detector doesn't register a wave-like phenomenon, sort of like a distribution of different amounts of energy at different places in the detector. No. Only one spot on the detector registers a hit. A dot appears on the detector. So, I mean, this is the strange situation we're in, where there is definitely some kind of wave aspect and there's some kind of particle aspect of what's going on here. And what Robert is suggesting is that perhaps we should abandon the particle aspect. I am sympathetic to that. One hypothesis that I entertain, I don't even know if this rises to the level of a hypothesis, but one line of thought I entertain is that really all of these entities, all of these matter, electrons, protons, neutrons, are really waves in the ether. And what we call particles are a particular way that the waves interact with one another. So if you think about the electron ramming into a detector screen, the detector screen is made of waves. If this hypothesis is true, it would be made of matter waves, and the light and the electron itself would be a matter wave. And perhaps the way that these waves interact with one another, when the electron wave hits the detector set, the set of waves that are the detector, somehow it gets smushed into a small location. And so what we call particles is really just the result of some kind of specific interaction among the waves. And really what's fundamental are these waves in the ether. And all there is this ether, and and what we call entities are just sets of waves in the ether. That's a hypothesis I take very seriously. Schrodinger himself thought along these lines. It's just a hypothesis, though. But it's something we need to entertain. We don't need to. I think we do need to entertain the possibility that particles are not fundamental, that they're a result of deeper facts about physical existence. That doesn't mean particles aren't real. It means that the particle, a lot of times people will say that, drives me nuts. The particles are real, like we know that. We see the interactions that are particle-like, but it would just be that they were a result of deeper wave-like phenomena or deeper phenomena of some kind that we have not yet understood.
And in philosophy of physics, there is definitely an idea that we don't have concepts yet to express what are those entities that are the causes of the observed phenomena.
That's an interesting idea. I hadn't thought of that before. Like, what happens if we simply, like, something that Francis Bacon said is that he said identifying the form of a phenomena. Bacon's concept of form is something like cause, but it's more like identifying the underlying nature of something. So, for example, Bacon correctly hypothesized that the form of heat is internal motion. That was a correct hypothesis that he put forward. And he put it forward as a hypothesis, which was right. He was insistent that he didn't know for sure. But anyway, so Bacon says that the way we identify forms, or the way we identify underlying natures, is by thinking of the natures that we are currently aware of. So, for example, Bacon was already, of course, aware of motion. And he attributed that concept of motion as being the underlying form of heat. And so, one concern would be, like, do we simply not have a stock of prior concepts which would allow us to ascribe form to these phenomena? I don't think so. It's something I should think about, though, because if that's really the case, it means we got to move on to something else as scientists for the time being before we're ready to think about these issues. But I don't think so, because a lot of the apparent form of these phenomena is the form of oscillations in a medium. Like quantum phenomena have the form of a wave. Light has the form of a wave. And like waves have mediums. So the next question is, what's the nature of the medium? And there is reason to believe that by making inferences from the known ways that these oscillations interact with one another, there's a reason to think that we could make inferences from those behaviors into the nature of the medium, and then conduct additional observations to prove that that is in fact the inner nature of the medium. It has been done before with Maxwell, and it can be done again at a deeper level, I believe. So further questions from the audience?
Or not only questions, if you want to raise an interesting thought or anything, let's
and especially objections, because I'd be interested, and I'm very interested in objections to what I've said here, because a lot of it is controversial, and I want the opportunity to answer questions that will come up to people when they hear these controversial views, so that I can strengthen my view even more, or find out that I'm wrong. Maybe you can show me I'm wrong.
So yeah, I had the same thoughts on your in relation to the display or screen was detecting like a particle or wave, i.e. the Young's double slit experiment is key.
Yeah.
I always thought that there was an underlining structure like you do. It's just the phenomena, a single slit versus a double slit, of why the diffraction occurs in that diffraction pattern. So I was thinking the same lines, that when the particle, like electron or photon, was transmit or shot at the screen, shot through this single or double slit, that those occurred because of the fact that it was not as a emergent property of the structure, like you said, the ether. It amplified, let's say, it's just showing us the background. If you see, there's two wavelengths or two frequencies interact on that screen. So I don't know if your thoughts of that.
I don't. Is this a question or a comment? I didn't follow.
Yeah, it's more of a comment
way.
or your thoughts. So yeah, because.
So I don't understand. Can you word the comment a different way?
So like I said, in the double slit, the pattern occurs on the screen based on the interaction between the wave as it goes as it emerges from the two slits. So and they do the whole thing is, okay, then they shoot electrons and it does the same thing. So how can a particle, I still I don't believe that there's the electron splits into two, and then interferes with itself. That's the whole pilot wave to me would be something that could occur. I mean, that could be just an example that we're proving that the pilot wave is along with the particle. So, and that's what we see on the screen, is the interference pattern is that. So
I think I agree with your way of thinking about this. If I'm understanding it, here's how I would reword it. You can tell me if I'm getting you right. So, in the double slit experiment, waves impinge upon two slits. They then emerge from two slits. the two waves then interlap with one another so as to constructively and destructively interfere. At certain places on the detector screen, they cancel with one another. At other places, they augment one another. And so that really is a wave-like phenomena. On the other hand, particles arrive at the screen one at a time. So that seems like a friggin' particle-like phenomena. So which is it? And one, now, the idea that the interference is caused by individual electrons splitting up into two electrons or something, then like randomly bouncing off of the inside of the inside of the slits, then bouncing off one another so as to create this pattern on the screen, that is really arbitrary. We're not going to entertain that, or at the very least, we're going to entertain that possibility last. A pilot wave theory, on the other hand, is very plausible, that it's simply the waves interfere with one another going through the slits, and so that creates certain patterns of where the particles arrive, because the wave pushes the particles around, and so as the wave interferes with itself going through the slits, which waves can, that's not weird, the waves interfere with one another, and that creates a differing distribution of how the particles end up being arranged on the screen. So like in short, the pilot wave theory has a shot of being correct. It is not yet proven in my mind, but it is consistent with all the observations. But something I would say is, just because a theory is consistent with all of the observations, that does not prove the theory on its own. We need to prove theories through a very particular method, which, by the way, is found in my book on induction, which is available on my Patreon page. So if you want to know my view on how to actually prove scientific theories, you can actually get a hold of that book by going to patreon.com/Inductica. If you want a copy of that book, you can start supporting the channel. Did that address your comment, Greg?
Yes, it did.
Cool. So let's move on to Bruce. Bruce asks, what was the response to Lorentz's response to the Michelson-Morley conclusion? How did the consensus evolve? Okay, good question. So we have a response to a response. So let me work this out in my head here, what that means. So Lorentz responded to the Michelson-Morley experiment with his ether theory. And Bruce asks, basically, what was the response to Lorentz's ether theory? I don't know. I don't know the history well enough to know exactly how people responded to it. All I know is the end result, which is that Einstein's theory of relativity was accepted instead. I do not find it surprising that Einstein's theory was accepted instead, because at the time, scientists were generally positivists. They believed that it was what Arkadiusz was saying earlier, which is that people accepted a philosophy of science that said that science should only serve to catalog observations. It should not delve into the underlying forms, as Bacon would call them, or the underlying causes, or the underlying nature of phenomena. And Lorentz's theory does that. It makes a hypothesis about the underlying causes of why these observations are different, and why the speed of light is measured to be the same for all observers. Instead, Einstein simply postulated that the speed of light is measured the same for all observers, and he deduced the rest of all physical phenomena in this field from that fact. And that was considered just as good as Lorentz's theory, if not better, because it's simpler. And the desire to identify underlying causes, since it wasn't there or it was even frowned upon, made Einstein's theory preferable to the physicists at the time. So Bruce, you can ask a follow-up question, or we can open it to further questions before we end the event. And I'm happy to, if we do have more questions, I'm happy to extend the time of the event a little bit to get to all these questions, but it depends on how many questions we have. Feel free to leave if you got somewhere to go, though. Okay, a new question from Robert. When two bricks are cemented together, we have two entities and a relation between them. Yes. When two electrons combine is a new single entity created? Yeah, that's an interesting question. This is actually a really good question. It gets into a lot of deeper issues. Let me start by talking about the two bricks. So again, what Robert said, when we have two bricks, you put some cement in there, you smush them together, you have two entities with a relationship. Yeah, that's true. But in another sense, you now have one entity. You truly have one entity. If I were to take, imagine the cement dried. If I were to take this dual brick and then throw it would be thrown as a single entity, right? There are other respects in which this is still two entities. So for example, if I were to maybe take a hammer and hit it, then the bricks would be likely to be separated along the line of the concrete joining member. And in that sense, they really act as two entities. But I think there's a sense in which even the bricks act as a single entity once they are cemented together. And an electron, now consider an electron going around a hydrogen atom. So really that's a proton with an electron not going around it, because it's not literally like the solar system, but somehow waving around it. Is that one entity or two entities? Well, I think it's the same story. In one sense, it's one entity, and in another sense, it's two entities. We need both perspectives. And what this all now let's say one more thing. Imagine that we put two electrons in the cloud of a hydrogen atom. So we have now one proton, two electrons. These two electrons form a kind of joint quantum state. Again with the computer mishearing her name. So imagine so when we have two electrons sharing a quantum state, there's a sense in which they now really act. They gain properties that they wouldn't have had if they weren't in there together. So I think that's the kind of situation that's motivating Robert to say, hey, shouldn't we think of two electrons as one single entity? Another example of this kind of thing would be entanglement. When you relate two particles in a certain way, it seems like when you change one, it changes another instantaneously, or the two have like properties that are inseparable. And so a lot of people, what they'll say is like, really, these two entangled particles are just really one entity. All of these are really important questions, basically, is what I'll say for now, because there's too much to get into right now. But what I will do is I will say that my theory of induction includes a theory of broad physical categories. So what the hell is that? Broad physical categories are the most broad concepts that we use when reasoning about the physical world. So examples of these concepts are entity, property, relationship, cause, effect, and there's a lot of other ones. And you'll notice that Robert's question relies on an understanding of what an entity really is. And in my theory of induction, I talk about these concepts and give a description of what the word entity should mean, why it should mean that, why if we think of entities in a certain way, which is a little bit controversial the way I think about entities, I talk about why we should think about entities in that way and how it allows us to grasp a greater set of facts if we think about entities in that way. And so what I believe is that a lot of the way we think about physics relies on the way we conceptualize these broad physical categories. And so work has to be done in order to clarify the broad physical categories so that they can be used to reason about these extremely abstractly grasped deep physical effects. Without an understanding of what we mean by entity, we're just not going to be able to reason about this stuff. So I have a video on the Inductica channel, by the way, called Broad Physical Categories. You can watch that. And you can also go to patreon.com/Inductica. And if you just support the channel at $30 for 1 month, then you'll get a copy of the theory of induction. You'll be able to read that part. That is part of my theory of induction, is a theory of broad physical categories. So as I said, we need to do a lot of work there, and I've done much of the initial work in that field. So further questions? We got a thumbs up. Robert's giving me the thumbs up for my question, for my answer. As I said, we can continue with more questions. Don't feel free to leave if you got other places to go. It won't hurt my feelings. Let's give a couple more minutes or a couple more seconds for people to think of any last questions. And if they can't, then we'll end. So it's looking like that's what everyone has to say. Anything else you'd like to ask or add at the end, Arkadiusz?
Actually, I wanted to ask you, what are your thoughts on, I suspect what those are, but I think it would be great to discuss this more in public. What are your thoughts on the multiverse interpretation?
So, okay, I'm going to give you my knee-jerk thoughts first, and then I'm going to give you some thoughts that occurred later to me. So my knee-jerk thought on the multiverse interpretation is, you can kind of see it on my face. I think it's a joke. I think it's ridiculous. I think it's, again, this is my knee-jerk response. So it's a joke. It's ridiculous. It's a sign of how sick our scientific culture is, that people would entertain an arbitrary hypothesis that could never have proof, that could never in a million years have proof for it, because we got these inaccessible other, existences that are somehow giving rise to quantum phenomena. And, again, my thinking is, okay, basically, this is an arbitrary hypothesis. Someone watched too many science fiction movies. They thought maybe that thing I saw in the science fiction movie is the cause of this quantum phenomena. And it is, and there's some sense in which it is consistent. Like, I can see some kind of causal line from the multiverse to these particular quantum phenomena. And since the deduction makes sense, maybe it's true. This is absolutely barbaric reasoning. You could just as easily say, oh, why are there all these, it's the same kind of thinking that leads a caveman to say, oh, there are all these bright lights in the sky. What are those? Well, maybe there's a giant dark blanket and a hummingbird poked holes in the blanket, and then we're just seeing like the holes, lead to some bright thing. So it's just some arbitrary BS thing you came up with. If it were true, it would explain the observations. This is more advanced than that caveman story, but it still basically has the same form. You came up with something. If it were true, it would explain the observations. But that is the most primitive excuse for science that exists. It's the way people thought far before science was ever invented. Okay, so that's my knee-jerk response. Certain people I respect entertain the many worlds interpretation, so that makes me slow my roll a little bit and makes me reconsider my knee-jerk response. One thing that might save the many worlds interpretation from no, let's not say it that way. Another thing to consider is to think of the many worlds interpretation of quantum. Think about what they're actually asking, and then remove the name, basically. Forget about the whole idea of many universes. That's just it becomes more plausible if you just remove that name. Okay, like, what are they saying? They're saying that they're not saying that there are many universes in the sense that, in this universe, Wolverine was killed. In that universe, Wolverine was not killed. And no, they're not talking. And then, maybe we can go to that one and steal Wolverine and bring him back to this universe. So we have a Wolverine in this. This is all from the comic books where they have many universes. They're not talking about that shit. That's not like it's a more scientific, it is a more scientific theory than that. I don't know about much more, but it's more than that. Here's what they're saying. They're saying that existence itself consists of a wave function, a big wave function, okay? And all the details of that wave function can be found throughout the vast expanse of the universe, okay? And different parts of the wave function branch off into different parts. And we only see part of that branching effect, basically. So when you that's different from what we would normally think of as a multiverse, because our acquaintance with multiverses is from fiction. So their proposal is much more like, because multiverse tends to mean this thing that we associate with fiction, it might be better to call it like a branching wave function model of existence, and saying that all of these possibilities of the wave function really exist all at once. And yeah, you could call that many universes as a shortcut, but that introduces a lot of baggage from fiction that we don't want to really label that theory with. And so that gives the theory a little bit more credit. However, my previous epistemological criticism still applies. This is the idea that the wave function really exists, like really does exist, and all the branches still exist at all times. That is an arbitrary hypothesis. It's more scientifically subtle than the hypothesis that a hummingbird is poking holes in a blanket, but it's basically of the same species. It's an arbitrary hypothesis to say that this wave function has actual physical reality, and then to say that all of its branches really do exist. That is an arbitrary hypothesis that is not motivated by any kind of prior evidence. It is simply that same kind of primitive reasoning where you come up with some kind of hypothesis and say, if that was true, then that would explain, then that would explain what we're seeing. No, like there are specific standards that a hypothesis has to meet to even be considered as a hypothesis. They can be found in my theory of induction. And simply explaining the phenomena that you see so far is not a valid way to put forward a hypothesis. By my standards, you don't get to just put forward anything you'd like as a hypothesis. The hypothesis needs to meet certain standards in order to even be validly considered as a hypothesis. The alternative is an infinite multiplication of hypotheses. We could create an infinite number of variants of this multiverse story, of the hummingbird story. There's an infinite conceivable number of stories, of arbitrary stories we could invent that are consistent with the observations so far. That is not the right way to do science. So I think at the end of the day, my harsh criticism still applies, though maybe not quite the vitriolic part where they're acting like savages. But I think it's still like at the very fundamental level, it still is the same faulty way of thinking. So yeah, any other questions, Ark, or anyone else?
I don't have any. If anyone has or wants to say anything, you're free to do so. If not, we can wrap up.
I just have one real quick on
Yeah.
that multi-dimensional theory. It sounds a lot like something I heard maybe a decade ago about instead of multi-dimensions, multiverse, but multi-dimensions. But it said something like 5th, 6th, 7th, 8th dimensions, and as you move beyond our 3rd dimension, it jumps into a dimension where you can't see it, can't measure it, and then it falls back into our dimension where it's measurable again. Is that kind of the same thing that they're proposing with that multiverse theory?
Good question. These are very much distinct. These are two distinct faulty ideas. When they talk about multiple dimensions, that is probably, extra dimensions. That is string theory. And what they mean by dimension in this case, they don't mean like another world or universe. What they mean is additional directions. So like, we have three spatial dimensions. You can go this way and that way, and then you can go up and down. These are our different directions of moving. What they mean by extra dimensions is they mean extra directions of movement. They don't mean extra universes. So that is a different but very much flawed, it's still just as flawed theory. All of that comes from string theory, which is also, from what I understand, I need to take that back. I have not studied string theory, so I really don't know, but I've heard a lot of convincing arguments that it too is basically an arbitrary hypothesis, which is consistent with the results. And so it again goes back to that primitive way of thinking. So that's what they're talking about with the extra dimensions. Fortunately, string theory has been discredited of late, so it's not something I need to worry about too much anymore. Well, I wouldn't have worried about it either way. Maybe it's something Arkadiusz doesn't have to worry about anymore. Good question. Yeah, it's an important clarification.
Arkadiusz, it looks like you're on mute and you're speaking.
Oh, thank you. Oh, thank you. Yeah, so if no one has any more questions or issues to raise up, I think we can wrap up. And from my end, first of all, if anyone wants to delve further and start with some philosophy of physics and read a book that has some quite a bit philosophy references, I can definitely recommend a book called What is Real by Adam Becker. And secondly, I would like to thank a lot James for appearing on today's salon. Thank you so much for coming and discussing. We'll see. Maybe we'll have more of those in the future. And yeah, thanks a lot. And I hope you've enjoyed it too. I definitely did. I hope everyone did. And thanks everyone for attending and your time.
Thanks, Ark, and thanks everyone for showing up.
You're welcome. Thanks, James. Thanks.
Thank you, everyone. Have a great rest of the day, and see you maybe in some next salon. Thank you.
You too. Thank you. Sounds good. Bye.
Bye.
Thank you.